I'd like to introduce Bob Sinkovits, who is our Director of Education and Training and has a huge, impressive background in all things HPC. And today he'll talk about his view of HPC by talking about parallel computing concepts, which I'm sure you'll find valuable. Bob, I'll turn it over to you.
Great, thank you so much, Mary. Let me just get my slides shared.
And I see your talk.
All right, look good?
Looks good to me, yes. Can everybody
Great.
else see the talk and hear Bob?
Yes.
All right, great.
All
Let's
right,
go.
thank you. I will kick things off. Thank you so much for joining us today for the first Expanse webinar of the year. This is actually one of my favorite topics in high performance computing. It's a very introductory level talk, but I'm hoping that you'll still find it interesting. And the topic is parallel computing concepts. And I have a GitHub repo that I'm going to be sharing with the group at the end, with a few exercises that you can work through on your own. So a quick overview of what I'm going to be talking about today. I'll start off with an introduction, and then I'll get into processes, threads, MPI and OpenMP. We'll then talk a little bit about hybrid parallel applications, and then Amdahl's law, other limits on the scalability of parallel applications, how to run parallel applications and complete scaling studies, and finally where to go next and some conclusions, a little wrap up from the talk. So this session is intended for anybody who currently runs, plans to run, or is thinking about running applications on parallel computers. If you write proposals for computer time on campus clusters, nationally allocated systems, or other resources. If you purchase time on compute resources, say going to the cloud, and you want to maximize your return on investment. If you're thinking about purchasing hardware for your lab. And finally, if you're just curious about parallel computing. So a little bit of motivation for the talk is, over the years, we've done lots and lots of training here at the Supercomputer Center. But here, and I think we see the same pattern in a lot of the other academic supercomputing centers, is that a lot of the training in parallel computing is really targeted at people who are programmers, who are writing their own parallel applications, and the topics tend to be heavy on things like MPI and OpenMP, CUDA, profiling application, performance tuning. All very important topics. But again, if you are not writing your own code, if you're more of an end user of the supercomputers, you really don't need these topics. But as a consequence, if you're an end user, if you're using somebody else's climate and weather or chemistry or phylogenetics or material science code, you may not get a proper introduction to parallel computing. So even if you don't write code, it's still important that you understand at least some of the basic principles of parallel computing so that you make the most effective use of this valuable advanced infrastructure. So I want to dispel a few of the myths surrounding parallel computing. And the first one is that parallel computing is for astrophysicists, engineers, climate modelers, and others who are working in traditionally math-intensive fields. And while this might have been partially true decades ago, today nearly every field of research makes use of parallel computing. And this includes the social sciences, life sciences, arts and humanities, in addition to physics, chemistry, engineering, material science, and the other domains that we refer to as the usual suspect. So to share a story from about 10 years ago, I was leading a tour of our data center. And one of the people on the tour was with the political science department here at UC San Diego. And he was amazed with the tour, looking at all the hardware, and he said, boy, I wish I could have access to this. And we realized that was a little bit of a failing on our part to really communicate that these are widely available resources and that they're available to everybody. Okay, another myth that we have with parallel computing is that throwing more hardware at a problem will automatically reduce the time to solution. So parallel computing is only going to help if you already have an application that has been written to take advantage of the parallel hardware. We've had cases here in the past when somebody had a serial application and they tried running it in parallel on a supercomputer. What they ended up doing was running the same code, the same problem, the same data multiple times. Essentially, they were repeating their work rather than running in parallel. So if you do want to use parallel computing, you do have to have a code that's been parallelized. And then finally, even if you do have a parallel code, there's going to be an inherent limit on scalability, and we'll be talking about that a little bit later in the talk. Okay, one caveat though about throwing more hardware at your problem is that there's things called high throughput computing workloads that can use parallel computing to run many single core GPU instances of an application so that you achieve near perfect scaling. This is more of a special case. Imagine that you're doing say many similar calculations, except each with a different set of inputs. Say you're doing a parameter study, and this is a case where you really can scale. You can scale up very far as long as you have enough work, as long as there are enough individual problems to be solved. And then finally, and the most important myth that I want to dispel for this group is that you need to be a programmer or a software developer to make use of parallel computing. So most users of parallel computers are not programmers. This is different than the situation, say, 20 or 30 years ago, where if you're doing parallel computing, you pretty much had to write your own. But now in many areas, there's mature third-party software out there that's been developed elsewhere and then made available to the community. So many of you, in fact, most of our users are now running somebody else's code. So if you're doing, say, weather modeling, you might use WRF. If you're doing molecular dynamics simulations of biological systems, you may use Amber or GROMACS or NAMD or other packages that are out there. If you're doing phylogenetics, this is the construction of phylogenetic trees showing the relationship between organisms. There's a whole host of software out there that we make available through a interface called the Cypress Science Gateway. If you're doing electronic structure calculations, you might use CP2K, VASP, and other software. So overall, most of you are probably going to be using somebody else's code. Now, parallel computers, I'm sure a lot of you are familiar with this already, but modern clusters and parallel computers consist of multiple compute nodes connected by a fast network. Now, the hardware that goes into these nodes is probably familiar to you already. It's the CPUs, the GPUs that you may have in your desktop or laptop system. Typically, each of these CPU nodes is going to contain one or more, typically 2 multi-core processors, and the GPU nodes will usually contain 4. And in order to use this hardware, we need applications that have been parallelized so they can run on multiple cores or multiple GPUs. And we're interested both in running across multiple cores or GPUs within a node and across multiple nodes. So, and what I'm showing here on the right is just a diagram, high-level diagram of Expanse, our current supercomputer, just showing the overall organization into nodes, racks, and so on. Okay, so I'm going to start getting into a little bit of the more technical content. We're going to shift gears. We're going to talk about processes, threads, MPI, and OpenMP. So you probably heard about processes and threads before. This is often a fuzzy concept for most folks who aren't deep into parallel computing or computer science. So these are both independent sequences of execution. You could think of a process as an instance of a program with access to its own memory, state, and file descriptors. So when we are running an MPI application, which we'll be talking about in a few minutes, you could think of this as being many independent copies of that program running on their own and then occasionally communicating. Threads, on the other hand, are very lightweight entities that execute inside a process. So every process is going to have at least one thread, And then those threads within a process can access memory. And we're going to find that threads and processes are both very, very powerful when we're trying to run a parallel application. So if you want to go a little bit deeper into threads and processes, I found a few online resources describing the difference and when you would use one or the other. Um, two that I particularly like is one here from Stack Overflow that really discusses in depth the difference between a thread and a process. I'll warn you, this is Stack Overflow, so the description is going to be a little bit nerdier, maybe aimed more to computer science community, but still pretty useful. And then the second link gives a much more informal description of the processes and threads. So compare a little bit more comparing processes and threads. Processes, a downside of a process is that it incurs more overhead. But on the other hand, they're more flexible. Multiple processes can be run within a compute node, or more importantly, you can run multiple processes across multiple compute nodes, what we call distributed memory parallel programming. If you really want to take advantage of the full power of a large supercomputer, you will need to use processes and some sort of parallelization scheme such as MPI. Now, threads I mentioned earlier, they incur less overhead. When we use threaded codes, we can use less memory since the threads within a process can have access to the same data structure. Now, from a programming point of view, thread level programming can be a little more complicated, or sorry, not more complicated, but there are some more nuances that could result in incorrect code. But that's really a burden on the part of the developer. The big downside of threads, though, is that they're less flexible than processes. So multiple threads within a process can only be run within a compute node, within a shared memory node. And let me just check the chat real quick, see if there are any questions in there. Okay. Oh, question here from Johnny Powell. How about books on the issue? Johnny, I will follow up with that later. I don't have any resources off the top of my head, but I'll do a little bit of research of that after I'm done with my talk. Okay, so a little bit more about processes and threads and why do I care about the distinction? So the type of parallelization will determine how and where you can run your code. So the distributed memory applications, again, multiple processes, multiple instances of a program, this can be run on one or more nodes. The shared memory applications have to be run within a single node. Now we also have what we call hybrid applications that use a combination of threads and processes. They can be run on one or more nodes, but we need to consider the balance between threads and process. And then finally, in all cases, we need to be aware how processes and threads are mapped and bound to cores. So in addition to all that, being aware of threads and processes, this is going to help you understand how your code is utilized in the hardware and identify some common problems. So I know that this is not a presentation for programmers. This is for end users of supercomputers. But I do want to talk a little bit about MPI, the message passing interface, and OpenMP. So MPI is a standard for parallelizing C, C++, and Fortran code so that they can run on distributed memory, basically multiple compute node systems. So while it's not officially adopted by any of the major standard bodies, it's really the de facto standard for a lot of large-scale parallel computing. De facto basically means that it's pretty much used everywhere. Now, there's a little bit of confusion once we start talking about OpenMPI, MVAPIC, and MPIC. These are just multiple open source implementations of MPI. So basically, MPI is a standard, OpenMPI, MVAPIC, MPIC, and these other groups, along with vendor-supported versions, will implement MPI. When you build a parallel application that's based on MPI, you could select which MPI library you're going to use. Now, MPI applications, I've said already, can be run within a shared memory node. And when they do that, all of the major MPI implementations are optimized to take advantage of that faster intranode communication. MPI is portable, it can be used pretty much anywhere. And although MPI is synonymous with distributed memory parallelization, there are other options out there that are gaining some adoption, like Charm++, which is used in the NAMD molecular dynamics package, UPC, and X10. And just a little bit of diversion for those of you who are doing deep learning. So although we're discussing MPI, the same principles are going to apply when you're parallelizing deep learning applications, say using Horovod, which is a distributed deep learning training framework that can be used with TensorFlow, Keras, PyTorch, and Apache MXNet, and Nickel, which is the NVIDIA Collective Communication Library, which implements multiple GPU and multi-node communication primitives that are optimized for the NVIDIA GPUs. So we're going to take a quick glance at an MPI application. We'll start with a really simple code snippet. Again, if you're not a programmer, you don't need to worry about the details. I just wanted to give you a chance to see what MPI looks like. So this is a, if you've ever taken a C or C++ programming class, you probably started off with Hello World. I have a main program. It prints the Hello World message, and then it terminates. So MPI applications, they're pretty dense. They're written at a low level. If you're a C programmer, MPI will look, I guess I'm going to say it would look not too bad. But if you've been working with higher level languages such as Python or Java, it may seem a little abstract. MPI is basically used to explicitly communicate data between processes using calls to the MPI library routine. So if you're not a programmer or an application developer, you do not need to know MPI. You just need to be aware that it exists, and that if you're building your executable, you'll need to use the appropriate wrappers. So to show you what a MPI version of that code looks like, in this case, we've added the code and the directives that we'll need in order to run Hello World in parallel. So instead of just simply printing out Hello World, we're going to have each process write Hello World, and it's going to tell us which process number it is out of how many. So this is this might be a little bit of an extreme case in the ratio of MPI to the original code, because we had to implement all of the initialization routine. We had to create the MPI environment, get the number of processes, get the rank of the process, get the name of each processor, and so on. But every MPI application is going to have some of this code. Again, if you're not a programmer, you don't need to know about the details of MPI. You just need to know that it exists. Now, OpenMP is an application programming interface, or API, for shared memory programming. And it's also available for C, C++, and Fortran. So OpenMP gives you a collection of compiler directives, library routines, and environment variables. It is supported by all of the major compilers, including IBM, Intel, GCC, PGI, and the AMD Optimizing Compiler Collection, or AOCC. It's portable, it can be used anywhere. And now, although OpenMP is often synonymous with shared memory parallelization, there are other options out there. There's a language which is you could think of it as an extension to C called Silk. That there's POSIX threads, which is a little bit lower level, and there are specialized libraries for Python, R, and other programming languages. So like we did for MPI, we're not going to get into the details, but I just want to show you what an OpenMP application looks like. If you're not a programmer, you could ignore this content. If you have a little bit of programming experience, though, this is a C implementation of a simple loop, of a couple of simple loops, where we take two arrays, A and B, and we initialize them, and then we add them element by element and store them in array C. So applications parallelized using OpenMP tend to be more readable, since they often involve relatively minor changes to the code. Again, if you're not a programmer, you do not need to know OpenMP, but you do need to be aware that if you have a code that's been parallelized using OpenMP and you need to build your own executable, that you're going to need to use the appropriate compiler flags. And unfortunately, these vary from compiler to compiler. On the next slide, we show what it looks like when we parallelize this code. This is a really a toy example. Adding 1,000, sorry, yeah, adding 1,000 elements of an array, element by element, isn't going to take much time. We would never need to parallelize this code. But if we did, and we're showing here how we could add a few directives, or in case of C and C++, pragmas, in order to parallelize that loop. Again, you don't need to know the details. You just need to be aware if your code is parallelized using OpenMP so that you build it correctly. So the big picture, MPI and OpenMP. On the left, we talk about processes and processes and MPI. So multiple processes are managed using MPI, and MPI is implemented in libraries. So if you're building an MPI application, you just need to link the appropriate library, MPICH, MVAPICH, OpenMP, or a vendor implementation. Threads, on the other hand, multiple threads are managed using OpenMP, and OpenMP is implemented by the compiler. So again, GCC, Intel, PGI, AOCC. In fact, over the years, I've never seen a compiler that does not support OpenMP. Okay, so we're going to move on now to hybrid applications. So many modern parallel applications are built using a hybrid approach to take advantage of both distributed and shared memory. And this often involves some combination of, say, MPI and OpenMP, although other combinations are possible. So hybrid codes have advantages over purely shared or purely distributed memory applications. So shared memory apps can have limited scalability within a node and cannot be run across multiple nodes. Distributed memory applications, on the other hand, may have higher memory requirements and more overhead when running within a node. So we'll find, especially as the number of cores in a processor has grown over the years, that these hybrid applications are becoming more and more common. So we're going to look at a very simplified parallel computer. So we're going to imagine a very, very stripped down cluster consisting of just 2 nodes, each of these with 16 cores, and they're joined by a network. So the large gray box is going to be our node. Those little blue boxes are going to be the cores within a node. And we have some kind of interconnect. It could be Ethernet or InfiniBand. So if we have a pure message passing application, so say just parallelize using MPI, we would run typically 1 process per core. And this example shows how an application running 32 processes could be executed onto 16 core nodes. So again, we have 1 process running on each core. If we have a threaded application, on the other hand, a pure threaded application, we would have just a single process, and all of those threads would be executing within that process. And then applications that have been parallelized using threading only, they're going to be restricted to running within a single node. And here we show a threaded app running 16 threads and 16 cores. Now I have an asterisk here. It says that technically any programming model can be mapped to any hardware. In fact, we had done this on one of our supercomputers a few generations ago. If you go back to the Gordon years, and we used something called VSMP, which gave you the illusion of a large shared memory space, but for the most part, the performance is pretty poor. And I don't know of any really good implementations of shared memory parallelism across, or threaded parallelism across multiple nodes anymore. So essentially, you're going to be running on a single node. Now, if we have a hybrid application, again, typically MPI plus OpenMP, we can use any combination of threads and processes within a node. So this example shows 2 processes per node and 8 threads per process. So you can see that on each node, we have two of those orange rectangles, which are processes, and then our 8 threads within the process. So for hybrid applications, a typical scenario is to run one process per node and use threads within a node, although this is becoming a little less common as the number of cores on a node continues to grow. So really, we can tune the dial anywhere from one process per node to one process per core if we have these hybrid applications. And this is where it gets a little tricky, trying to figure out how we choose the balance between processes and threads, given that we have this range of options. And the only way to really know for sure is to do a benchmarking study. You might want to try this with different number of threads per process, look at the runtimes and the memory usage. So again, we can tune this anywhere from one process per node and one thread per core, all the way down to one process per core. And let me just check the chat real quick. Oh, so and a question here from Iman Mandel. Are core and thread the same? So no, they're not. A core is a hardware concept. So it's one of the execution units within the processor. It's a CPU. A thread is a programming concept. It's a thread of execution. And as I mentioned near the beginning of the talk, multiple threads can access the same shared memory structures. We're going to move on to Amdahl's law. We'll talk a little bit about the scalability of parallel applications. So Amdahl's law describes the absolute limit on the speedup of a code as a function of the proportion of the code that can be parallelized and the number of processes. So this is really the most fundamental law of parallel computing. So let's let P be the fraction of the work that can be parallelized, and S be the fraction of the work that must be run sequentially. So you can imagine a lot of workloads where there's a certain amount of serial work. It might be the input or output. It might be the aggregation results from multiple threads or processes that really just can't be parallelized. Whereas P again is the fraction that we can take, fraction of work that we can take that we can divide up across multiple processes. And then N is going to be the number of processes. So our speed up is going to be 1 over 1 minus P plus P over N. So in the limit as the number of processes goes to infinity, the theoretical speed up is going to depend only on the proportion of the parallel content. So again, here we show N going to infinity. The P over N term that vanishes, we're left with 1 over 1 minus P or 1 over S. So you might be looking at this and say, that doesn't seem so bad, but we'll show in the next slide that it doesn't take much serial content to quickly impact the speed up. So this is a plot that I generated showing Amdahl's law for code with 50, 75, 90, and 95% parallel content. So on the y-axis, we are showing the speed up of that application. And on the x-axis, the number of cores. You can see it for the bottom curve, which is a code with 50% parallel content that we very, very quickly level out. Of course, we are going to not get any better speed up than 2x. The green curve shows 75% content. Again, we quickly level off. Our maximum speed up is going to be 4. But look at that, even with 95% parallel content, we can only get a maximum speed up of 20. If we go out further, in this case, I added a curve showing a code with 99% parallelizable content. Even there, if we're running on a single node with 128 cores, that's typically what you'll find on expanse, bridges at the Pittsburgh Supercomputing Center and other clusters. Even with the code with 99% parallelizable content, even though we could get a maximum speed up, of 100, if we're using all 120 of those cores, we're making terrible use of that node. So basically, we would be using 128 cores, but only getting a speed up of about 60.
Bob, there's a question in the chat about threads.
Yeah. Yeah, so a question from Peter. So would it be correct to say that threads are executed on cores? Yes. So we would take threads and we would map them to cores. And typically you would execute one core, one thread on each core. Although you can map multiple threads per core, but it will typically impact the performance.
There's a question about are cores and threads the same?
Oh, and yeah, Marianne, I addressed that one earlier. Yeah.
Okay,
So
sorry about
again,
that.
no problem. Yeah. So core is a, as I mentioned, is a hardware concept, whereas thread is a programming construct. Okay, so we're going to talk about some of the other limits in scalability. So Amdahl's law, which we just discussed, sets a theoretical upper limit on the speed up, but there are going to be other factors that affect scalability. There's going to be communications overhead. There's going to be limitations based on the problem size. And we're also going to be impacted by uneven load balancing, how well we could take the work and divide it up evenly across the processing units. So in real life applications involve communications and synchronization. Say when all the threads of the processes have to complete their work before proceeding, or irregular problems, non-Cartesian grids, the speed up can be much less than what was predicted by Amdahl's law. So we'll start off with load balancing. So when we parallelize a code, we need to take the work, we need to divide it up into chunks that can be executed independently, either by threads or processes or a combination of the two. Now, if the work cannot be distributed evenly, then processes are going to sit idle, waiting for the longest chunk to finish. And this is going to be a really common situation when you're working with irregular domains, more complex geometries and so on. So let's say that we're running on a system that has 4 CPUs or cores. We're going to label them here 0, 1, 2, and 3. We're going to start off, we're going to take the available work and we're going to divide it up across those 4 CPUs. The blue regions are when that core is busy, and the red hatched regions are when it's idle. So we'll see that if we had a load imbalance, say CPU 2 was given a larger chunk of work than 0, 1, or 3, it's going to take longer to finish, and the other CPUs are going to be waiting. They're going to be idle, waiting for CPU 2 to finish its work until we get to that synchronization point. Now we take the next chunks of work, we divide it up. In this case, it was CPU 1 who got the largest chunk. In this case, 0, 2, and 3 are going to be sitting idle. So this is going to affect the scalability of your application. So we have. All right, we also have the issue of communications overhead. This is an example showing a very idealized case solving a system of partial differential equations. So if you're doing computational fluid dynamics, magnetohydrodynamics, climate, weather, a lot of other types of simulations, they involve solving systems of partial differential equations on a grid. And that grid is then distributed across processes to achieve parallelization. So this is obviously a toy problem, very, very simplified. We're solving a system of PDEs on a 16 by 16 grid. And if we wanted to run this on 4 processors, we're going to divide that into 4 evenly sized 8 by 8 chunks. We'll call this process 0, 1, 2, and 3. Now, if we assume that each cell is updated using the values of the 4 neighboring cells, then the cells that are within the interior of each chunk can be done completely within the process. But when we get to the cells at the boundary, they're going to need data belonging to a different process. And this is when we need to explicitly communicate that data. So to accommodate this, first of all, we need to add a halo of ghost cells, and then the data has to be communicated between those processes. So the data movement, the amount of time it takes to do this, is going to depend on the latency and the bandwidth of the network, and this is going to introduce communications overhead. So again, as a end user rather than a programmer, you're not going to be responsible for implementing this. This is going to be done all under the hood in the application, but you just need to be aware of the impact that this is going to have. So for the cells that are the boundaries of the chunk, data belonging to the neighborhood process is needed. And I'm showing here the pattern of communication that we're going to have. So each process is going to be sending data and receiving data from its neighbors. Let me just check the chat and see. You here. All right, so yeah, so going back to Lauren, yes, so Marty answered that already. So as a user, I don't want to tell my parallel software to use more threads than the total number, and typically that's correct. And then Johnny Powell asked, perhaps you will get to this question, but how does one manage uneven loads in say in Charm++? So I'm not terribly familiar with Charm++, but in general, whether it's OpenMP, MPI, Charm++, you're going to do some dynamic scheduling of the work. So as an extreme example, I had worked on an application years ago in computational finance where we were analyzing all of the stocks that were traded within a given day. And there's a orders of magnitude difference in the amount of work that was required for each stock. Say something that traded heavily like Apple or Google required a lot of work, others didn't require much. So what we would do is we would start with the largest chunks of work. We would hand it out to cores or processes, and then when they were done, they would grab the next available piece of work. So depending on the problem, you could do this dynamic load balancing. And then Summeron had followed up with Lauren's question. Yeah, so and Marty said yes, sometimes is the operative word. Yeah, that's sometimes you can use more threads than cores, especially if you have random patterns of memory access and you're really waiting, you're spending a lot of time waiting for data. But in general, in HPC applications, you're probably going to stick to one thread per core. Sorry, Caitlin Hetherington asked, is a process the same thing as a node? And I'm sorry, I'm kind of mixing up my terminology a little bit. Now, you think of a node as being a computer, like the whole box. It can contain multiple processors, each with multiple cores or CPUs. And then finally, Shanfeng Ma, for OpenMP, is there any historic reason to call it open multiprocess instead of open multi-threading? Now, I have to be honest, I've never heard OpenMP referred to either of those. I've only ever heard it called OpenMP, so I need to look into that a little bit more. Okay, so moving on. So we talked about the limits imposed by Amdahl's law, and then all these other factors that are going to affect scalability. So by now you're probably wondering, how does anybody ever use all the cores on a single modern compute node, let alone the full power of large supercomputer? So first of all, the reality is that most parallel applications do not scale to thousands or even hundreds of cores. In fact, on Expanse, we have many, many jobs that just run within a single node or even use a fraction of that node. Now, if you do want to achieve higher scalability, though, there are several strategies. We do have these large machines out there, sometimes will be dedicated to a single large calculation. So first of all, we can grow the problem size with the numbers of cores or nodes. If you look into something called Gustafson's law, it addresses the issue of weak scaling, where we allow the problem size to grow so that each thread or MPI process has the same amount of work, but we just grow the problem as we grow the number of cores. We can overlap the communication with computation. Again, this is something that's being done by the developer. If they're highly skilled, very, very clever, they can be doing work while they're waiting for the communication to finish. I already talked about the third bullet, that we could use dynamic load balancing to assign work to cores as they become idle, and we can increase the ratio of computation to communication. So a good example is if you're familiar with computational fluid dynamics. If we extend that to combustion, or what we call reactive flow, the chemistry calculations within each cell are very computationally expensive, and that's going to increase the computation and communications, and we can often get better scaling in those situations. Okay. So running parallel applications and scaling studies, this is going to be the last major topic before we wrap up. So we've covered the basics of parallel computing: hardware, threads, processes, hybrid application, the implementations, MPI and OpenMP, Amdahl's law, and other factors that affect scalability. So we've got all this theory and background, but how do we know how many CPUs or GPUs to use when we're running our parallel application? And the only way to definitively answer that question is to perform a scaling study where a representative problem is run on a different number of processes. And by a representative problem, I mean one with the same size, say the grid dimensions, number of particles, number of images, number of genomes, etc., and the complexity, the level of theory, the type of analysis, the physics, as the research problem you want to solve. Now, this doesn't mean that you need to run your entire production scale calculation to do the scaling study. If you're doing, say, molecular dynamics or solving systems of partial differential equations, you could run just a few time steps instead of a large number of time steps. If you're doing high throughput computing, you could run just a few problems in your parameter sweep rather than the entire sweep. But you do want to do a limited number of these calculations just to figure out how much faster your code is running as you use more hardware. So I'm going to talk about presenting the scaling results, and we're going to start off with the wrong way to do this. So these two plots, believe it or not, they are scaling curves for two different codes. And it's really hard to tell which one has the better scaling behavior. And the reason we can't tell is because the timings at the large core counts are indistinguishable. So we see this a lot in the allocation proposals, asking for time on our supercomputers. We'll get these plots on these linear axes, and it's really, really hard for us to tell if you are using the parallel hardware effectively. So a better way to do this, the way that we like to see scaling studies presented, is to plot the data on log axes. So now, again, these are the same. These are the same data sets that I showed on the previous slide, but note the different scales for the left axes on the two plots. I've also included a line, that's that short black line, showing linear scaling and plotting the parallel efficiency on the right axis. So in this case, for a perfectly scaling code, which I show on the left, we'll see that the efficiency is going to be pegged out at 1. And if we look at runtime as a function of number of cores, we have this linear relationship, and you see that it has the same slope as the black line that I added. Now on the right, I'm showing the code with a more limited scalability, and you'll see that the runtime starts off decreasing linearly with the number of cores, but eventually it flattens out. And if we plot this in terms of the efficiency, we could see that after we get past about 16 cores, that the efficiency is rapidly dropping off. Okay. So then the question is, where should I be running on this scaling curve? So if your work is not particularly sensitive to the time to complete a single run, consider using a CPU or a GPU count that's at or very close to 100% efficiency. And sometimes this might mean running on a single core or GPU. This is going to really make sense for parameter sweep workloads where the same calculation is run many times with different sets of inputs. Now you can go a little bit further out in the scaling curve if the job would take an unreasonably long time at lower core counts, or if a shorter time to solution helps you make research in your, helps you make progress in your research. So we don't want to wait. We often don't want to wait days or sometimes even hours for our results. So if running at a little bit lower efficiency makes you more effective, if you do a calculation, you come back in 15 minutes, look at the results, make an adjustment, run it again. Yeah, you definitely want to run at a lower parallel efficiency so you get quicker turnaround. If your code does not have checkpoint restart capabilities and the runtime would exceed the queue limits, you may have no choice but to run at higher core counts. And then sometimes the time to solution is absolutely critical. And in that case, it's okay to run at lower efficiency. So examples might include calculations that need to run on a regular schedule. Say you're collecting data each day, it needs to be processed and analyzed overnight. You need those results in the morning. Or, and we hope you wouldn't be using our supercomputers for this kind of work. But if you're doing work like severe weather forecasting, where you need an almost immediate response, say we're looking at response to a tornado or tsunami or so on, yeah, then you can keep using more and more cores until as long as your runtime continues to decrease. Okay, one other consideration is some applications have a very large memory footprint. So on resources like Expanse at SDSC or Bridges 2 at Pittsburgh Supercomputing Center, they allow multiple jobs to share a node. And these jobs can normally request, without extra charge, memory in proportion to the core count. So for example, Expanse has 128 cores and 256 gigabytes of memory per node. So you get, without any extra charge, to 2 gigabytes per core. But if memory is the limited resource, you may need to throw extra cores at it to get that extra memory, and it could result in poorer scaling. But do consider using specialized large memory nodes when they're available. And then finally, going to wrap up. We've only scratched the surface. SDSC has many training resources on a wide range of topics. We also have user guides for the nationally allocated resources. They contain a lot of information on job submission, accounting, compilation, data movement, available software, and other site-specific content. So I have here the link to Expanse and also the link to Access, the Access documentation. If you're not familiar already, Access is the follow-on to Exceed, and they have the user guides for all the resource providers. So to wrap up, parallel computing is for anyone who wants to accomplish more research and solve more challenging problems. You don't need to be a programmer, but you do need to know some of the fundamentals to effectively use parallel computers. Remember that processes could be thought of as instances of a program. Threads run within a process and access shared data. MPI and OpenMP, these are just implementations of parallelization schemes that are used to generate the parallel software. In terms of scalability, always be aware of Amdahl's law, but also know that it gives you an upper limit on the scalability. And there are other factors that can impact the scalability, such as load imbalance and communications overhead. And then finally, know how to display your scaling data and choose core counts. And then finally, if you're interested, and I will paste this into the chat, I have a Python notebook that I use to generate the figures in this presentation. In fact, you may want to use the notebook to generate your own scaling plots to in your next allocation request. And with that, I'm going to wrap up, and I'm happy to take any questions. Great, thank you, Johnny. So I'm going to do a quick demo of my Jupyter notebooks on the bottom here. Does anybody have any questions first?
Yeah. Hey there. So a question that's maybe about the cores versus threads confusion. If I do something like run htop, it tells me I have 64 CPUs, but I'm sure my computer only actually has 32 cores. What's the discrepancy there?
Ooh, so some processors like Intel will implement what they call, I believe in Intel, it's called hyper-threading. Yep. And Marty put it in there, where it's executing 2 hardware threads per core. And hyper-threading often gives you better performance for a lot of business applications, but we generally turn it off on our systems. Yes, and Marty added, yes, logical versus physical cores.
Okay, so I stop seeing any kind of speed up once I get into that, like past the number of cores. I can keep
Right.
going to the number of threads, but yeah, okay. Thank you.
Yep. And Trevor added, yeah, you can run 100,024 threads and 32 cores. They will be time sliced by the kernel and will not run at full speed. So again, we typically turn off hyperthreading in HPC environments, but it's often turned on for running business applications. Right, so I'm going to, I have a note here, and I realized that I misspoke a little bit when I was talking about large memory, when we're discussing, running at no additional cost. It's actually a little bit more complicated than that. You can separately request cores and memory, and you'll be charged in proportion to the larger resource they use. So for example, even if you only request 1 core, but you need half the memory on the node, you would be charged essentially for using half of that node. Now, what I did mean to imply there, though, was that if you do have a large memory application and you're out in the regime where where you're getting into lower efficiency, that you may want to let's say take advantage of those cores that you're essentially being charged for. But we can follow up on that. And then finally, let me do just a quick demo here. Okay, and Mary or Cindy, can you confirm that you're seeing my browser now?
Yes, I can see your notebook.
Okay, so let me just take this. I'm going to paste this into the chat. Sorry, I meant to do this earlier. So if you go to my repo, I have a Jupyter notebook, and then a few figures that I generated for this presentation. So if you're familiar with Python, you should be able to easily adapt my notebook to generate your own scaling plots. These are the ones that I want you to ignore. Here I'm showing the scaling using linear axes. I scroll down a little bit and I show the proper scaling using logarithmic axes. So this was the figure that you saw earlier for a code with perfect scalability, and then a more realistic case of a code that has limited scalability. If you want to play around with Amdahl's law, down here I have the code that I use for generating these plots. And in fact, let's add one more. We'll add one more line in there. And this is for a code with 99.9% parallel content. So if you want, you can go in here, you can play around with the different ways of plotting your scaling data and experiment with Amdahl's law. I'm going to go ahead and stop sharing. So are there any questions before we wrap up? All right, if not, thank you so much for coming. I'm going to hand things back to Mary Thomas to close the session.